Okay, that's it for the introduction. So can you please take over the session? Thank you, sir.
Thank you, Ayush. Good evening, everybody. Am I audible and screen is visible as well?
Yes, so you're audible and screen is perfectly visible.
Okay.
Thank you, sir.
So let's start. Right. So again, we have during last demo there was some problem from my side. So let's start from beginning. So this course, the title for this course is Methods for Manual Analysis, STAAD.Pro and ETABS, right? So let's start with this demo session. So these are the objectives for the course, that to make you certain about the basics. Make you certain about the basics of theory of structures, then to make you proficient in manual methods of structure analysis, to make you confident in modeling and analysis using STAAD.Pro. So the thing is that why manual methods? Because when it comes to structure design, I have explained it in previous demo, and I'm doing it again. The thing is that again, the basic difference between AutoCAD and these softwares like STAAD and ETABS and so on, that is, AutoCAD is a drafting software, ArchiCAD is a drafting software, and these are design softwares, right? Please turn off your mics, right? So that is the case. Now, when in case of a drafting software, anyone can do drafting, you know. If somebody, I mean, all you need to know is how this particular program works, the commands and all. And if you have to draw a rectangle on your computer screen, you can do it. But when it comes to design, you have to be an engineer. That is the major difference between a drafting software and a design software. So if you are not an engineer, no matter how much you know, if you are attending this course or any other course, but whatever you are designing, if you can't verify it, then your design is not complete. Your analysis is not complete, right? So that's where these manual methods come into play. And most of students, including me back in the day, we don't really care about these manual methods when we are doing our BTech and all. We are just going through these methods just to, you know, clear our exams and all. But when you come to field, these methods are really going to come in handy. So that is why we have included manual methods, and that is the, I mean, initial part of this course. Then to make you confident in modeling and analysis and modeling and analysis using STAAD.Pro and ETABS. So that is the objective. And prerequisite is that the student attending this course should be at least aware of basic knowledge of mechanics. Okay? So moving on, this is the course content for first and second week. It is all about manual analysis. It includes basic things like bending moment and shear force. Then comes sprint fixed beams. Then comes moment distribution method. We have included this method for manual analysis because this is the most used method when it comes to manual analysis, right? Slope deflection, conjugate beam method, they are all fine methods, but they have their limitations. But when it comes to moment distribution method, you can employ this method for any kind of frames. Especially, it is going to be cumbersome. It depends upon how complicated your frame structure is, but you are going to get very much approximate answers from moment distribution method. And this method is the most I mean, before the advent of these softwares, this method is the how to say, it is a big backbone of all analysis and design when it comes to structural engineering, right? So that is why moment distribution method. Then lastly comes building frames, how to implement this moment distribution methods onto building frames. And moment distribution method is going to give you analysis for vertical loads. What about horizontal loads? So that we have to that we are going to undergo under this topic, building frames. Next, then we will move on to software part of our course, introduction and understanding the STAAD.Pro way of doing job, creating geometry using different tools and methods, defining cross sections of structural elements, constant, and so on. And then after defining load systems in STAAD.Pro, then same is the case for ETABS, right? So this is our course content. Now let's start the, I mean, you all, this is a demo, so I have to give you a demo about my teaching prowess. So let's go with, let's start it. So introduction to basics. So again, applied mechanics, first of all. So force, the term force and resultant force. If like force, what is force? Resultant force is fine. You have more than one force, then you have to find a resultant of it. That is fine. But what is force? So force is defined as an agent which produces to or tends to produce, destroys or tends to destroy motion, right? So if a structure, if a body is in a stationary position, that doesn't mean there is no force acting on it. As a physicist, as an engineer, definitely there is some force acting on it. What is happening is that all these forces are canceling each other. That is why there is no motion in that body. That is what force is, right? And if a body is moving, then definitely there is all the forces which are acting on that on this particular body. One of the force, it is superseding all other forces. So that is why this particular body is moving in a certain direction, because of that, because a force in that direction is superseding all other forces. So this is how force works. Then resultant force, if a number of forces etc. are acting simultaneously on a particle, then a single force which will produce the same effects as that of all the given forces, known as resultant force. Whether the forces are cancelling each other, or whether one force is superseding all other force and there is a motion in the body, there's always going to, you have to find out resultant force. So that is it. Then comes moment of a force. Now what exactly is a moment of a force? It is a turning effect produced by a force in a body on which it acts. So moment of a force is basically a force, when a force acts on a certain, okay, in order to explain it properly, let's so this is our beam, right? And this is these are the supports. These are the supports to this beam, and there is a force acting somewhere here. So now this is a force for this particular section. For this section, not this section, sorry, not this one, but for the very section on which this force is acting, this is going to act as a force. But if you move a bit right or left to this this particular section, let's say up to this point, at this point the effect of this force is going to be considered as a moment that you have to make that you have to be clear about. If we are, for example, if we are moving at this section, so now effect of this force at this particular section is going to be it's going to be termed as moment or moment of force. And how you are going to calculate it? The value for this force into the distance, that is going to give you the moment at this particular section, right? So as I mean, this is the, let's say this is at A, sorry, yeah, this is distance A from this particular end, right? So, and this is force F, this is force F. So, and let's say this is X, this distance is X. Okay, so F into X will give us the moment at this particular section, F into X. And then we are moving up to this point, you are going to get F into A. So if you are moving away from the very section on which force is acting, as you are moving further away, the value of moment is going to be increased. So that is what a moment is. Okay, so then after that, then the again basic this includes in basic mechanics conditions of equations of equilibrium of any system of force. So if a particular structure, if a particular body or a structure is stable, so that means it is satisfying these three equations: summation of H is equal to 0, summation of V is equal to 0, summation of M is equal to 0. If we are talking about two-dimensional assembly, right? So all the horizontal forces, its sum has to be 0. All the vertical forces, its sum has to be 0, and all the moments, its sum has to be 0, in order to ensure the stability of a 2D frame. Let's say 2D frame, right? So that is conditions of equations of equilibrium. Then comes stress. So now what is stress? Again, back to this, back to that beam. There is a force acting on that beam, right? Now, it is not just going to deform. The beam is not just going to deform. It is going to offer some resistance to that force, which is trying to deform that particular section. That resistance is called stress. That resistance, that inherent resistance of your structural element is called stress. So stress is the resistance to deformation per unit area due to the action of external force, right? So mathematically, it is small p is equal to capital P upon A. Capital P is force, and area is the unit area on which this force is acting. So that gives us stress. Then comes strain. Now let's say this force F is acting on this particular section. First, your element is resisting deformation due to that force, but that force is gradually increasing or its resistance is gradually decreasing. Anything can be the case. So like for after a certain time, after a certain period, there will be some deformation in your beam. So that deformation is, if you want to quantify that deformation, then we have this term strain. Strain is the deformation per unit length. Strain is the deformation per unit length. So stress and strain. Then comes elasticity. Now, if that particular section is offering stress to external force, it is due to its stiffness. The term is stiffness. That stress is due to its stiffness. Stiffness is, I mean, if we are like term stiff, that means something, let's say, I mean, in vernacular, it's something hard, something tough to deform in certain direction, right? If you have a log in your hand and you want to break it and it is not breaking, then it is stiff, or you are not providing enough force to break it. So it's stiffness. So that is stiffness, right? Now, opposite to stiffness is elasticity. Opposite to stiffness is elasticity. But stiffness is something resisting, stiffness is the property which is resisting deformation. But when it comes to elasticity, elasticity is something, okay, the definition says elasticity is the property by virtue of which a deformed body springs back to its original position. That is not the case with stiffness. If if you are, again, about that log, if you are trying to break up that log and you are providing enough force to it and you overcome its stiffness, it is going to break. Now it cannot be whole again. So that is stiffness. But in case of elasticity, you are deforming something, and when that external force is removed, it springs back into its original position. That is what elasticity is. Now everything, all the matter in universe, it has some elasticity, right? It depends. Elasticity how much, what is the value, what is the proportion of elasticity? When it comes to a rubber band, it is significantly elastic. But when we are talking about concrete, it is also elastic, not as much as a rubber band, but there is some elasticity to concrete as well. So that is elasticity. Then deformation of a body. So delta I is equal to P into I upon A into E. So P upon A is stiffness, sorry, stress into I upon E, that is deformation of a body. Then comes modulus of section. So now, okay, modulus of section is the quantity obtained by dividing the moment of inertia of a body about its center of gravity by the distance of the extreme fiber from the centroidal axis and is denoted by Z. So that is modulus of section. If I want to define it right now, then I have to explain moment of inertia and so on, but we can't do it right now. But why I put this term here? Because it is going to be very important when it comes to analysis and design. Modulus of section is going to be, we have to use, whether you are doing it manually or whether you are using a software, you have to use this term. You have to have the value for Z, modulus of section. So keep that in mind. We are going to use it. Then comes types of structure. So, okay, what are the basic types of structures? So all the structures are, they are categorized into these two types: statically determinate and statically indeterminate. So statically determinate structure, again, you can find these structures in your laboratory, right? But in the real world, I hardly doubt you are going to come across something statically the structure as a whole is statically determinate. Okay. A particular element of an assembly, it can, but not an assembly in a whole. So what is statically determinate structure? So if the forces in the members of a structure as well as reaction can be found by the conditions of equilibrium or the principle of statics alone, it is known as a statically determinate structure. Means you are applying external force on a particular, like the beam we have, I explained on it before. You are applying a force onto that beam. Now there is going to be some deformation in that beam. There is going to be some reaction at its end. So in order to find out all these values, if you are able to find out all these values using these three equations, summation H is equal to 0, V is equal to 0, and summation M equal to 0. If these equations can satisfy your assembly, then your structure is statically determinate, right? It is not going to happen when you are in real world structures. It is not going to happen. Then comes statically indeterminate structure. So statically indeterminate structure, the very basic example of statically indeterminate structure is a fixed beam. A fixed beam is a statically indeterminate structure. So this how much common statically indeterminate structure is. So what is statically indeterminate structure? Now, if the forces of the members of a structure as well as its reactions cannot be found out by the conditions of equilibrium, if those three equations, summation as H is equal to 0, summation V is equal to 0, summation M is equal to 0, if you cannot resolve your element or your structure by use of those three equations, and you are going to need more than that, then your structure is going to be statically indeterminate structure. It is known as statically indeterminate structure or redundant structure. Now those three equations, along with those three equations, you have to go for deformation equations as well. So now your structure is statically indeterminate. Now again, statically indeterminate structure, it has two types: internally indeterminate and externally indeterminate structures. So that is it. Now comes supports. So like if we are talking about a beam, right? A beam is not a beam until unless it is resting on to some support, right? For example, let's say you end up casting a beam and it is resting on a ground. That beam, you end up casting a RCC beam or a PCC, right, precast section, and it is resting on the ground. And now you have to analyze it. So in order to analyze that particular element in that particular beam, you have to define its supports. If it's resting on a ground, then it is on continuous support, right? It is on elastic. It's on elastic support. So that is, support is something which makes which really completes a structure. Without any support, without defining any support, without assuming any support, you cannot analyze any element, any assembly, any structure, right? So For example, like in STAAD or ETABS, you have modeled a particular structure, particular frame structure, right? And you forget to provide restraints to its base columns or whatever you are creating at its base. You forget to provide any restraints to it, whether it's simply supported or it's fixed, it doesn't matter. And you run analysis, then you are going to get, no, your structure is not stable because it is not resting on anything. If there is no support, there is no structure and there is no analysis. So that's how important supports are. So basically we have these three types of supports: roller, pin, and fixed, right? Roller is also known as movable hinge, pin is immovable hinge, and fixed is fixed. So what is happening in roller support? As you can see, this is a beam section and this is a beam and section of it is resting on this roller. Now, of course, it cannot move upwards. Oh, sorry, it cannot move up and down, right? That movement is restricted. But because it's a roller, it can move to and fro. It can move to and fro. And because it's a roller, and so this beam can rotate around it. The end of this beam, it can rotate around this support, right? So that means, so the only obstruction we are providing is up and vertical movement. So we end up with one reaction. Then comes pin support. Now this roller is replaced by this pin. So what is happening? Again, vertical movement is not allowed. Now we are obstructing its to and fro movement as well. So we end up with another reaction. Now we have two reactions. But still it can rotate around this support. It can rotate, the section can rotate around the support. So we end up with two reactions. So what I'm trying to say is, in case of structural analysis, if you are obstructing something, right? If you are obstructing something, then there is going to be some reaction to it. And if there is going to be some reaction, you have to find out what will be that reaction. Okay? So this is the very, I mean, if you want to break structural analysis to its very core, so this is what is happening. What is happening is we are obstructing, like when we are talking about foundation. Let's say the column, and this column is finally ends up into a foundation. So what is happening? We are restricting its movement in all three-dimensional directions, right? If we are providing isolated footing, then it cannot move to and fro. It cannot move vertically as well, and it cannot rotate. So now you have to find out, you obstruct its movement. All 6 degrees of movement is not allowed to that particular section. So you have to find out what will be the reactions due to this. So that is what structural analysis is in a nutshell. So now let's talk about fixed support. After pin support, we have fixed support. What is happening now in fixed support? No vertical motion, no to and fro movement, as well as if you look at this beam carefully, it is not allowed to rotate here. It is not even rotating. So I am obstructing its rotation along this direction, right? So what is happening? We end up with the moment in opposite direction. In order to obstruct this rotation, you have to provide a moment from yourself. आपको एक moment apply करना पड़ेगा to counter that rotation. ठीक है ना? This is what mathematically, this is how you do it. So you end up with this movement. So now we have 3 reactions, 2 reactions and 1 moment. So that is fixed support. So these are the basic supports. Moving on. Now comes bending moment and shear force. So moment is bending moment. Where when we are talking about moment, and along with moment, we are talking about a flexural element like a beam or a slab. So that moment is bending moment in that case, right? Why bending moment? Because that moment is causing bending. So that is why it's called bending moment. So, and then shear force. So bending implies deformation of a bar produced by loads perpendicular to its axis, right? Deformation of a bar produced by loads perpendicular to its axis. That is what bending is. Then comes plane bending and oblique bending. So if the plane of loading passes through, it's a typing error, passes through one of the principal centroidal axis of inertia. Of the cross section of the beam, the bending is said to be plane or direct, right? We have two major axes, one major and one minor, right? X and Y. In 2D, we have X and Y. So if the plane of bending is along either X or Y, then your bending is considered to be plane bending. But if that is not the case, if the plane of bending is somewhat skewed to either to your, I mean, it's up to you how you are going to consider it, but it's not coinciding with any major plane, any major axis, X or Y, and it's up to some angle. So that is now becomes oblique bending, plane bending and oblique bending. Then comes types of beams. So types of beams: cantilever, simply supported, and fixed beam. So this is cantilever beam, right? What is happening? We have this fixed end. We have this fixed end, and this one is free. So whatever force you are applying onto this end or anywhere in this section, what is going to be affected is this fixed end, right? This fixed end is going to affect. So all the action is going to be at this fixed end. It's like wherever you are providing obstruction, you have to solve all the reactions along that obstruction. So in this case, it is we are obstructing it on its one end. So this is what you call, cantilever beam, right? Then comes simply supported beam. So pinned and roller. It can be both pinned, both roller. Still, it's going to be known as simply supported. So in case of simply supported beam, what is happening? Now we have these two supports. So we have to find out reaction at these two ends. In case of this support, it is not, we are obstructing its vertical movement. So there is going to be one reaction. We are obstructing its to and fro movement as well. So there is going to be another reaction here. In case of this support, we are only obstructing vertical movement. So there will be one reaction here. So 1, 2, and 3 reactions. We end up with 3 reactions in this case. So this is what a simply supported beam is. Another thing is, when it comes to simply supported beam, you are applying some load onto it, right? And as a simply supported beam, what is going to happen? The rotation is going to start at this very point, right? The rotation of this beam, of this section and this section, starts from this very point. So due to this load, all the effect is going to be on this span. All the effect, I mean, whatever resistance this section beam is going to offer to this external loading, it is going to come from this span. So this is what a simply supported beam is. In that case, in case of if you are designing a simply supported beam, let's say if you are designing a RCC simply supported beam, you have to provide more, you have to provide much more reinforcement in its span. Okay? Contrary to it, when we are talking about fixed beam and this external loading is here, what is going to happen? There will be no rotation here and there will be no rotation here, right? So it is going to deform like somewhat like this. So in that case, what is going to happen? The deformation at its span, its middle span, is going to be significantly less than a simply supported beam. Why? Because these fixed ends are going to absorb some of the moment. These fixed ends are going to absorb some of the moment. So that is why if fixed beam is, in case of fixed beam, you are optimizing the use of your beam section as compared to any other form of beam. That is why when we are talking about RCC frame, most of the time you end up with fixed beams. Most of the time you end up with fixed beam. Because in case of RCC, what is happening is you are casting this beam and column junctions along with beam span and slab. So even if you are not, you are trying to provide provision in your reinforcement to make a certain beam in RCC frame structure as a simply supported beam, but because of the monolithic casting, there is going to be some amount of fixity to it. So you are now never going to end up with in case of RCC structure I'm talking about, right? I'm not talking about precast concrete. You can have simply supported structures, precast concrete. RCC, it's very hard to find very hard to create or cast a very, I mean, a pure simply supported or hinged connection. So these are the types of beams: fixed, simply supported, and cantilever, simply supported, and fixed. Now let's go to so first, STAAD.Pro. So STAAD.Pro is a tool for structural engineers. What is STAAD? Comes from S, T, A, and D. So that is the full form of STAAD, Structural Analysis and Design. It is the one of the first software application in the world, automating the work of structural engineers and liberating them from lengthy and tedious manual methods, hence enhancing their efficiency and boosting the construction industry altogether. So why and how STAAD is better? So let's consider this beam, right? It's a single bay, 2-story, 2D beam. In this case, for a simple 2D frame, the most appreciated method is moment distribution method. You can easily analyze this frame structure using moment distribution method, in which loads on the beams to be transferred to the supports at their ends. Whatever load is here, half of this has to be transferred at this end, half of it's going to be transferred to this end. Each support partakes the portion of loads as per its stiffness. Okay, you can transfer half of this load here, half of this load here, okay, depending upon its stiffness, right? If, for example, if the stiffness of this column is X and the stiffness of this column is 1.5X, so, and this is the loading, so the more stiff your element is, more load it's going to act toward itself, right? Keep that in mind. More stiff you are creating your particular element, or you are creating your overall structure, then it is going to attract more load towards it. Okay, na? So if this is 1.5X and this is X, then when it comes to the distribution of this load, it will be distributed along the proportion of their respective stiffnesses. Okay, keep that in mind. So this is how it works. Each support partakes the portion of load as per its stiffness. And what is stiffness? K is equal to E into I upon L. What is L? Length of your element, length of the particular element in consideration. I is moment of inertia. Where it comes from? It comes from the cross section of your element, and E is modulus of elasticity. Okay, from material, whatever material you are using, that provides you modulus of elasticity. So E into I upon L is K, which is stiffness. Now, in which only I of the section is variable, right? Whatever span is there, it is going to be there. You can't change the span, right? You have gone through, like in practical application, you are going to get a plan, an architecture. So you can't change the plan. The room is going to be this much wide and this much long. It is going to stay like, it is going to be like that. You can't change. Okay, I don't want to create that. I don't want to design a particular beam for this much span. So no, let's reduce its size. It can't be done. So length is going to be same. Then E, modulus of elasticity for particular material, it is going to be constant as well. What is variable is I. The section of the cross section of your element, it is variable. You can make it be more deep. You can make it more shallow. You can provide thickness to it, right? That is only variable. So that can be done. This can be analyzed using moment distribution method. But move into a 3D frame, and this method falls short in delivering the solution in an efficient manner. When we are moving into a 3D realm, what is going to happen? You can go through moment distribution method, but first it is going to be very tedious. Second, you are going to get conservative answers. The answers you are going to get, they are going to be more conservative, because without using finite element method, you cannot analyze a 3D frame. So, but if you are trying to do that, then it's better to be on conservative side. So whenever if you are using moment distribution method on a 3D frame, you end up with conservative answers. Now enters stiffness matrix method. This is finite element method, one of the types of element method, stiffness matrix method. So what do we have? Force matrix P is equal to stiffness matrix K into displacement matrix delta. In this case, force matrix is partially known. Why it is partially known? Because you are applying occupancy load. So occupancy load, where you are going to get the value for occupancy load, you are going to get these values from the code. Okay, you are designing, let's say you are designing a theater hall and you get your occupancy load values from a code. I mean, what is going to happen? What if the occupancy load somehow increases? You can't resist, like itne logo ke baad nahi, we are not giving you, we are not allowing anybody inside. This is not happening, right? So that is kind of partially known. Then comes displacement matrix. It is again partially known. It is again partially known because I mean, your load we are applying, we are considering which we are assuming this load is going to be acting on this particular structure, and because of this load, this will be the displacement. But again, if load is not, we are not certain about the load, how can we be certain about the displacement? So again, it is partially known. We are you know how much it is going to displace up to this value of load. But again, what the load increases, then what is going to happen? Again, displacement is going to be increase or decrease, whatever is going to happen to displacement. So you can't be certain about it. So it is partially known. Stiffness matrix is the only matrix which is fully known. Why it is fully known? Because span is up to you or up to architect, I mean whoever is planning this particular structure. Then material, again it's up to you what material you are going to use. You are going to use timber, you are going to use RCC, you are going to use PCC, you are going to use steel frame, right? So, and sections, again the sections of element, it's in your control. Whatever dimension you want to provide the cross section of the structure of these elements, you can do it. So stiffness matrix is the only matrix which is fully known, right? So we end up with these three matrices. So with above matrices, using the method, we can solve the system for unknowns. So we can get reactions, hence SFD, shear force diagram, and bending moment diagram can be generated. So what is happening with above matrices, using the method, we can solve the systems for unknowns. And so we can get reactions, hence shear force diagram and bending moment diagram can be generated. And with displacement of different nodes be known, the displaced and deflected shapes can be generated as well. Okay, so this is how you use stiffness matrix method, and this is how it simplifies things. As the case with all structural analysis method, this one is extremely tedious and is not feasible for manual calculation. But with STAAD, that is not the case anymore. So this, as good as this system is, this method is, if you are just trying to go for this method with a handheld calculator, it is not feasible. So that is why you need computers for that, and that's where STAAD or ETABS come into play. Now in case of STAAD, this will be the workflow. All these softwares, whether STAAD, ETABS, SAP, Procon, whatever software you are talking about, they all based on, like everything, I mean all computer applications, garbage in, garbage out basis. It all based on, all these softwares are based on garbage in, garbage out. Whatever you are feeding to it, the output depends, the quality of output depends upon quality of input, right? So input is very important. When it comes to using these softwares, input is very important. So input file, modeling the structure, you have to model the structure, you have to make sure that your model in this software is related to, as much as possible, it is related to the actual actual structure on the ground. So modeling the structure, then assuming and applying sections, confinements to the model. A section is like cross sections. Then comes confinement, I mean restraints to the model, and defining and applying loads on the model. So this all includes input file. Then sending this file to analysis engine. I mean, your work is done here. Your work is done here. All your expertise, all your experience, you are going to use in creating this model and make it as lifelike as possible. Then all you have to do, you have to send this file to analysis engine. Then you are going to get results, read the results and verifying these results. How to verify these results? You are going to verify these results using manual methods. Then sending the results to desired design engine. After these results are only analysis. Now you have to design for this analysis. So then send it to desired engine. That means send it to concrete design model, or send it to steel or any other design engine. So this is the workflow. Then comes, this is for STAAD. Now comes ETABS. So ETABS and STAAD, they are basically they are both design softwares. The basic difference between STAAD and ETABS is, as per my view, STAAD is a wholesome software, right? You can design you can analysis and design anything on STAAD. You can go for a bridge, you can go for a dome, you can go for a bunker, and you can go for a building structure as well. When it comes to ETABS, ETABS is a special purpose analysis design program developed specifically for building systems. When you are talking about ETABS, basically ETABS is a module of SAP. SAP 2000 is a software like STAAD. It's a mother software. ETABS is a building frame structure module taken away from SAP 2000 and then refined it. They refined it and then they packaged it as ETABS. That is what ETABS is. It's a special purpose analysis and design program developed specifically for building systems. It's sophisticated, yes, easy to use. When we are going for ETABS after STAAD, you come to know that it is very easy to use ETABS when you are dealing with frame structure, because ETABS can deal with frame structures. That's the limitation for ETABS. You cannot, you cannot design a bridge on ETABS, right? But instead you can do that as well. But when it comes to frame structure, ETABS has it has more commands, more ways of dealing with the frame structure as compared to STAAD. In ETABS, model definition is floor by floor, column by column, bay by bay, and wall by wall, instead of non-descript nodes and elements in general purpose programs. General purpose programs, that means STAAD.Pro or SAP 2000 in case of CSI. So this they just want to say this is not a general purpose program. So that is it. This makes structural definition simple, concise, and meaningful. That is what ETABS is. In most buildings, the dimension of the members are large in relation to the bay widths and story heights. Those dimensions have a significant effect on the stiffness of the frame. In most buildings, the dimension of the members are large in relation to the bay width and story heights. These dimensions have a significant effect on the stiffness of the frame. ETABS corrects are for such effects in the formulation of the member stiffness, unlike most general purpose programs that work on center line to center line dimension. Well, fine, they are putting it here, and I am using their literature, but that is STAAD is following the same method as well, right? And ETABS is a completely integrated system. This means that you can create only one model of the floor system and the vertical and lateral framing system to analyze and design the entire building. Now, that is a beneficial. Sorry, that is a it is a beneficial point when it comes to comparison between STAAD and ETABS. So the integrated modules include drafting module and model model generation, seismic and wind load generation module. When it comes to seismic and wind load generation, or when it comes to application of loads, ETABS is much better, or much easier, not better, it's much easier and efficient as compared to STAAD.Pro. You will notice it when we further this course. So I'm not saying that they are both same. There are some plus point with ETABS, and I personally use ETABS a lot, and SAP as well. So I am kind of biased towards CSI, but when it comes to, if you are modeling a certain structure in ETABS and analyzing and getting results for it, and you are modeling the same structure in STAAD, you are going to get very precise results for it from STAAD as well. But whatever is difference, the difference lies in when you are drafting, when you are creating this model. So in case of that, when you are using ETABS, again, it's my opinion, then you find it comparatively more user friendly than STAAD. Seismic and wind load generation module, then gravity load distribution module, finite element based linear static and dynamic analysis module, output display and report generation module, steel frame design, concrete frame design, composite beam design, steel joists design, and shear wall design module. And that concludes our demo. So that's it from my side for today. Now back to you, Ayush. Abdul, what book you are talking about, I don't know. You are saying how to get this book, but what book you are talking about?
Dear teacher.
Yeah, please go on.
Yes, I am from Somalia.
Right.
Okay, help me with this book and information.
I am not getting you. What book you are talking about?
This book? How I can get this book?
This book means this presentation.
Yes, presentation.
Okay, then you have to contact from Protrainy. They will. I am not capable of answering that question. They will let you know how to get this presentation.
Okay, bro. Thanks, dear teacher, and send me this presentation group.
Pardon?
Group. Send me presentation. Okay. Goodbye. Yeah.
Hello.
Okay.
Hello.
Yes.
Yeah, go on. Go on, please.
सर मुझे कुछ पूछना था.
हाँ बोलिए.
इस कोर्स में मतलब जो अभी आपने जो बताया था वो प्रेजेंटेशन में, वैसे ETAB और STAAD.Pro सिखाया जा रहा है, उसके साथ में मैनुअल डिजाइनिंग, लेकिन रियल लाइफ प्रोजेक्ट पे क्या बस थ्योरेटिकल जैसा है? हेलो.
Real life project. नहीं, we can include. Yeah, we are going to include the real life project. The project I am working on or I have worked on, उसको include करेंगे. Hello.
और
you are getting.
हेलो.
हाँ बोलिए.
और जो भी ETAB और STAAD.Pro में डिजाइन करेंगे उसका डिटेलिंग वगैरह वो नहीं सिखाएंगे, मतलब क्या AutoCAD में या फिर CSI डिटेलर वगैरह दूसरा कोई सॉफ्टवेयर?
डिटेलिंग CSI डिटेलिंग इज नॉट, नहीं वो इनक्लूड नहीं है यहाँ पे.
AutoCAD में डिटेलिंग, 2D डिटेलिंग.
Detailing is not the part of this course.
Yeah,
आवाज
teacher.
नहीं आ रहा है
CSI,
आपका प्रॉपर.
you are talking about software CSI detailing, so that is not included.
ओके, अगर CS डिटेलिंग नहीं है लेकिन ऑटोकैड में तो डिटेलिंग करना सिखाओगे ना उसमें.
AutoCAD भी इसका हिस्सा नहीं है, AutoCAD में भी डिटेलिंग नहीं बताई गई है. I can give you an example. I can provide you with an example of my own detailing that I can do on personal level. I can do that. कि भाई आप पूछ रहे तो अगर आप students कहते हैं तो I can explain it to them, but that is not the part of this course.
Teacher, hello.
Please go on.
Presentation, your recorded video.
I'm not getting you. What are saying?
Okay. Help me in this presentation.
Yeah, this presentation. What about this presentation? You want the video for this presentation? That's what you are talking about.
I want this presentation because I'm from Somalia. I learn civil engineering.
I get it. You are from Somalia, so you have to contact, someone from Protrainy. And I'm sure you have some group over there. Who is here from Protrainy with us right now? Ayush is here, or whoever is here.
Yes, sir.
ये इनका जो प्रॉब्लम है कि he wants this presentation or whatever, तो आप जरा देखें. I don't know if you
Yes,
can
sir. We
provide-
have shared in the chat the demo and the syllabus and everything we have shared in the chat. You can go through it.
Okay.
Okay.
Sharing this group.
Yeah, it's already
Okay.
shared. Anybody else?
Thank
Hello,
you,
sir.
teacher. Thank you, teacher.
हेलो सर.
या बोलिए मोहम्मद.
क्या सर इसमें फाउंडेशन स्ट्रैट फाउंडेशन भी इंक्लूड है आपके कोर्स में? थैंक यू.
Again, we are talking about frame structure. Foundation is